Hello everybody. Today we are going to continue our discussion of section 8.2 from your textbook, and we are going to focus on drawing valid Lewis dot structures. Before we begin, we need to review a few key concepts. The first thing that we need to review is that covalent bonds occur when electrons are shared by nonmetals. Now remember, why do atoms even bond to begin with? It's because they don't have a full set of 8 valence electrons, or an octet. Having an octet of valence electrons will cause you to be stable and to not have to react. The only group on the periodic table that has that naturally is the noble gases. So the rest of the nonmetals are going to choose to share their electrons until they have that full set of 8. In our previous reading and discussion, we have learned that there are 3 different types of covalent bonds, which I have organized into a table here for you. The first is a single bond. A single bond is represented using a single dash. It represents 2 electrons that are being shared, or one shared pair. It is the longest yet the weakest of the 3 types. Double bonds occur when 4 electrons are shared amongst 2 atoms, or we call that 2 shared pairs. And we use 2 lines, kind of like an equal sign. Double bonds are intermediate or medium in their length and in their strength. A triple bond is 3 dashes drawn between 2 atoms. 6 electrons total are shared. There are 3 shared pairs. Triple bonds are the shortest but the strongest of all 3 types. Now, as we begin drawing valid Lewis structures, some tips that are going to be very helpful. Hydrogen. Hydrogen can never be the central atom in a molecule because hydrogen can only hold 2 electrons total. So if we take a look at this diagram that I have drawn here, I put 1 hydrogen on the outside, and this dash right here shows me a single bond. Remember, a single bond represents 2 shared pairs according to our table. So this hydrogen has 2 electrons on it, which is good because the 2 electrons mean that it's stable. Now let's take a look at this oxygen. Over here on this side, it has, if we count the dots, there's 1, 2, 3, 4, 5, 6 dots, and then 7 and 8 electrons are included in this single bond here, because 1 dash stands for 2 dots. So if we look here, this oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it, which is good because everything would need an octet to be stable. We're trying to get to 8 electrons. Now, this hydrogen in the center, if we count, it has 2 electrons over here in this bond, and then a 3rd and a 4th electron in the other bond. That means it has 4 electrons total surrounding it, and that is bad because hydrogen can hold no more than 2 electrons. So you can only put hydrogen on the outside, like this hydrogen on the left. Halogens, remember those are group 17 elements: chlorine, fluorine, bromine, iodine, astatine. Halogens like to share just 1 pair of electrons, so they always go on the outside of the molecule. As we draw Lewis dot structures, our 2 guiding rules to see if we've drawn a correct structure are that you must use the correct total number of valence electrons, which is the first thing that we determine is our total budget or number of electrons that we have to work with. And when you're finished, each atom in the molecule has to have a full octet of electrons, except for hydrogen, which needs 2. All right. So let's begin. The first molecule that we're going to start with is CCl4, carbon tetrachloride. We'll learn to name that in another chapter. But if I want to draw the Lewis dot diagram for carbon tetrachloride, I must begin by determining my total number of electrons that I'm working with. So I list all of the elements that are in the compound. In this case, I have carbon and chlorine. There is 1 carbon because there's no subscript after carbon, and there are 4 chlorines. Then I take a look at my periodic table, go to the top of the column and see how many valence electrons are there in an atom of each of that. Carbon has 4 valence electrons, so 1 times 4 gives me 4. Each chlorine has 7 valence electrons. 4 times 7 is 28. 4 plus 28 is 32. So that means that when I'm done, I must use 32 total electrons in my structure. Now, as I go to draw this, remember earlier we said halogens like chlorine cannot be in the center. Carbon likes to be in the center. The other rule, if you can't decide what to put in the center, put the lone element, the element that's a singleton and there's only one of, in the middle. So I'm going to put carbon in the middle, and I'm going to draw 4 chlorines around it. Then I have to draw at least a single bond connecting each of these atoms, because they have to at least be sharing one pair of electrons to be a molecule. Now, I would suggest as you're drawing these that you draw them in pencil, because you're going to kind of have to figure this out by trial and error. If we look at the carbon in the center and we count up right now, it is surrounded by 2, 4, 6, 8 electrons, so it has a full octet. We don't need to draw any electron dots around it. If we go up here to this top chlorine, it has 2 electrons surrounding it right now, because 1 dash stands for 2 electrons. So I got to draw 3, 4, 5, 6, 7, 8, so that it has a full octet. I need to do the same thing to each of the other chlorines, because they also need full octets. All right, so then after I draw those dots, everything in my structure has a full octet, so that's rule 2. But did I follow my first rule and use the correct total number of electrons? So I need to go around and count these up to see if I've done this correctly. So let's start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. That's the correct number. So this is a valid Lewis structure. All right. Let's try for ammonia, NH3. So we're going to begin by tallying up the total number of valence electrons that we need in our structure. So I write that I have nitrogen and hydrogen in this molecule. There's 1 nitrogen, 3 hydrogens. Every nitrogen gives me 5 valence electrons. Again, you'll have to look at the periodic table, see what column the element is in to figure out its number of valence electrons. Every hydrogen contributes 1 valence electron, because hydrogen's in the first column, so 3 times 1 is 3. Then I add these up. 5 plus 3 gives me 8. So when I'm done, I need 8 valence electrons total in my structure. As I go to draw this, I'm going to put nitrogen in the center because it is a single atom. The other thing, remember, hydrogen can never be in the center of a molecule. Then I'm going to connect these with a single bond to begin. Now, if I take a look at this, every hydrogen has 1 dash around it, and the dash stands for 2 electrons, and hydrogen is full when it has that duet or 2 electrons, so that's good. But right now, nitrogen has 2, 4, 6 electrons around it, so I'd have to draw 7, 8 to give it a full octet. Everything now has an octet or a duet around it. And in total, did we use 8? Well, I have 2, 4, 6, 7, 8. Correct. Now, I do want to point out, this is a valid Lewis structure. Sometimes I see students draw like this. That is also a valid Lewis structure. It's just drawn upside down, but that's okay. What I'm looking at, do you have 3 hydrogens bonded to the nitrogen and a pair of dots on the nitrogen? Things that I don't want to see, I do not want to see something like this, where hydrogen's in the center, because then this hydrogen has way too many electrons around it. This nitrogen doesn't even have a full octet. If you were to try to fix that by drawing dots around it so that it has an octet, then you'd have 2, 4, 6, 8, 10, 12 electrons in your structure, which far exceeds your budget of 8. So that would not be correct. All right. Next, CO2. We're going to use the same method. I'm going to list that I have 1 carbon, 2 oxygens. Every carbon gives 4 valence electrons to the structure. Every oxygen gives 6. 2 times 6 is 12. 12 plus 4 means 16. So this time, I'm going to put the carbon in the center because it's the single atom. Then I'm going to draw my single dashes here. Then I have to fill out my octets. So this oxygen needs 6 dots around it in order to have a full octet. This oxygen right now has 2 electrons from the dash, so I would need to give it 6 dots. Then if we take a look at carbon, right now it has 2 electrons here, 2 more there, so that's 4, 5, 6, 7, 8. All right, so we now have given it a full octet, but did we use our total of 16 electrons? Well, let's count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Anyways, we're over budget. We used too many electrons. So what I suggest is go back, draw your 2 oxygens and your carbon, try a double bond on one side. When I try that double bond, this oxygen on the left now has 4 electrons around it from the double bond, so I'd have to draw 5, 6, 7, 8. The carbon right now has 6 electrons around it, so I'd have to draw 2 more dots to give it 8, and this oxygen needs 6 dots to get its octet. Now, if I tally up and count, I have used 2, 4, 6, 8, 10, 12, 14, 16, 18. Still not correct. What should we try next? Well, what about if we put double bonds to each of the oxygens? In this case, the left oxygen is going to need 4 dots around it, so will the right one. And if I count up around carbon right now, it's got 2, 4, 6, 8 electrons, so it has an octet without adding any dots to it. Did we use 16 total? 2, 4, 6, 8, 10, 12, 14, 16. We sure did. So this is why I said that I would make sure that you are using a pencil, because you're probably going to mess this up a few times before you get it right. And rather than erase the incorrect structures, I just like to draw an X through them. That way you can see exactly what you did that wasn't right. That way you're not just constantly spinning in circles, repeating the same mistakes over and over. Now, let's take a look at ozone here. Ozone is O3. It's found in our atmosphere and protects us from harmful UV rays from the sun. There's 3 oxygens. Each oxygen gives you 6 valence electrons. 3 times 6 means that we're going to need 18 valence electrons total. You've got 3 of the same element here, so you're just going to put them in a straight line. If I were to connect them with a single bond and fill out my octets here, the outer 2 oxygens are going to need 6 dots around them so that they have an octet. The center oxygen is only going to need 4 more dots drawn around it to get to 8. And then if I count up, I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have too many electrons. So to save us a little bit of time, I'm going to tell you that through trial and error here, we need to adjust a bit. And we are going to put, we're going to put a double bond on one of these oxygens. And then we need to fill out, the center oxygen would have 2 dots around it. The left oxygen needs 2 pairs. Now we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Everything has an octet. What about though if I drew it this way, where we have the double bond on the right side instead of the left? Is that valid? Well, as long as I get the proper number of dots drawn around it, that is valid. And these are what are called resonance structures. Resonance structures are different variations of arrangements for the same molecule, but they're both correct, all right? So there's more than one right answer. In fact, there's actually a 3rd resonance structure that's more complicated. What about if you put these in more of a triangular arrangement and you finished it out with dots like that? Kind of funky looking, but that, if you count them up, everything has a full set of 8 octet electrons, and you've used 18 total. So usually what we do is, you might notice here, I put brackets around each correct structure, and I put a 2-sided arrow in between, because in nature, you're gonna find all 3 of these versions out there. And the ozone that is in nature is gonna constantly be changing back and forth between the different correct forms, and it's gonna be a mixture of all of these. All right, so resonance structures just mean that you have more than one correct structure for the same molecule. The next thing that we need to talk about is polyatomic ions. The prefix poly means more than one atom, and it's an ion with a charge. So I've gone through here and I have listed the 10 polyatomic ions that are on your list: acetate, ammonium, carbonate, chlorate, cyanide, hydroxide, nitrate, nitrite, phosphate, sulfate, and I've given you the formulas here. Remember that for cations are positive, so that means electrons are lost. Anions, electrons are gained. That's how they become more negative. So how would I draw a Ballard-Lewis structure for a polyatomic ion like hydroxide? All right, we're going to use the same approach that we were earlier. We're going to list that we have oxygen and we have hydrogen. We have one oxygen, one hydrogen. Each oxygen gives you 6 valence electron. Each hydrogen gives you 1. So 6 plus 7 gives you, or 6 plus 1 gives you 7. Sorry, I got ahead of the game. But we had a -1 charge. And remember, negative charges mean that you have gained electrons. So we have to add on 1 extra electron for the charge of -1. So when I'm done with this, I need 8 total valence electrons. Okay, as I go to draw this, I would draw an oxygen and a hydrogen, and I'd connect them with one shared pair. Hydrogen can't get any more dots for a double bond to share because it's full. So then I fill out oxygen's octet by drawing 6 dots. If I count up, I have used 8 total electrons in my structure. The last thing that I need to do is put brackets around this and write minus. If it was a -2, you'd put -2 so that you can see that it is, in fact, an ion. All right, another polyatomic ion, carbonate. We've got 1 carbon, 3 oxygens. Each carbon gives you 4 valence electrons. Each oxygen gives you 6. 3 times 6 is 18. 18 plus 4 is 22. I'm gonna add on 2 electrons for the charge. So that means 24 electrons total when I've drawn this correct. I'm going to choose to put carbon in the center since it's the single element. I'm going to draw my 3 oxygens around it. Then I'm going to go through and I'm going to fill out the octet for everything. So each of the oxygens is going to need 6 dots. If I look at carbon right now, it's got 2, 4, 6 because it's got 3 bonds around it. So I have to put 7, 8. Now, did I use 24 total? Let's count up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I did not. You can kind of play around with this, but I'm going to go on ahead for the sake of time and tell you that to get the correct number of electrons, you're going to have to put a double bond on one of the oxygens. It really doesn't matter which one. There would be resonance structures like we just learned. And you're going to draw your brackets with a -2. So feel free to play around and prove to yourself that that is the correct structure. All right. The last thing that you're going to need to know in order to understand tonight's homework are the 2 main exceptions to the octet rule. The first exception I call the double your luck elements. The double your luck elements are beryllium and boron. They are satisfied when they end up with twice the number of valence electrons that they started with. So instead of needing 8 total valence electrons, sometimes they can be stable by just having twice what they start with. So if you look, beryllium's in the second column, so it normally has 2 valence electrons. It will be considered stable if it ends up with 4 valence electrons. Boron is in the third column, so as long as it doubles its 3 to 6, it can be considered stable. So the example that I would like for us to go through is BeCl2. So if I list, I've got 1 beryllium, I have 2 chlorines. Each beryllium gives me 2 valence electrons. Each chlorine gives me 7. 2 times 7 is 14, so 16. All right, I'm going to put beryllium in the center since it's the lone element. All right, then I'm going to finish out my octet of electrons here on my chlorines. Normally then I would go through and I would draw 2 more pairs of dots on beryllium so that it's got a full 8. If I count up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, I have overspent. Now, you could, in theory, try double bonds like this. And then finish out your octet for your chlorines. You've got 2, 4, 6, 8, 10, 12, 14, 16. However, even though that follows the rules that I told you earlier, this is no good. The reason why it's no good is, think of chlorine and the halogens as kind of like the bullies on the periodic table. They are super, super electronegative, and they only want to share one pair of electrons. That's it. Beryllium's kind of a weakling element when it comes to electronegativity. It is not assertive enough, electronegative enough, strong enough to force those chlorines to share 2 more pairs. So what happens is, beryllium's kind of like the poor little element that gets bullied by chlorine, and it says, here, chlorine, I'll share my electrons with you, but that'll give me 4 electrons, which is twice what I started with, and then we're just gonna call it good and be done at this point. You can share your 1 pair with me, and then I'm good, and we'll move on our way here. So if you count now, you've got 2, 4, 6, 8, 10, 12, 14, 16 total. The beryllium in the center only has 4, but that's okay because it's an exception to the octet rule. All right. The last thing that we need to discuss is what's called an expanded octet. Sometimes the elements sulfur, phosphorus, and the noble gases can hold more than 8 electrons in order to bond with halogens. Remember, if something expands, it like gets larger in size. So if I look at my example of PCl5, and we're going to try to draw a valid structure here. I have 1 phosphorus, 5 chlorines. Each phosphorus contributes 5 valence electrons. Each chlorine gives me 7. 5 times 7 is 35. 35 plus 5 is 40. So total in my structure, I need 40 total valence electrons. Now, I'm going to put phosphorus in the center because it's the lone element. And I am going to actually put the 5 chlorines all around the phosphorus. Now, this should at first alarm you, because if you count up now, whoops, this is terrible. If you count up now, the phosphorus in the center is surrounded by 10 total electrons, but that's okay. It's an expansion. It's going to expand to be able to hold these chlorines. Each chlorine needs 6 dots drawn around it, because the 6 dots plus the 1 shared pair that each of them has will give them their full octet. Remember, they're kind of the bullies of the periodic table, so they can force phosphorus and sulfur and noble gases into this arrangement in order to be stable. Then if I count up here, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. 40 total valence electrons. The chlorines are all satisfied, and the phosphorus has just expanded in order to satisfy everyone's octet. Please take time to go through these and practice them on your own, and then access Google Classroom in order to see the 8.2 worksheet that is assigned as homework tonight. For those of you that were in class, you received a paper copy.